Hello, everyone, and welcome to the Surveillance Advances Series' 2024 to 2025 season. This seminar series is co-hosted by the Public Health Agency of Canada and the National Collaborating Centre for Infectious Diseases, or NCCID. The title for today's seminar is Establishing a Surveillance, Early Warning, and Forecasting System for Avian Influenza Outbreaks in Canada. My name is Robert Sager, and I'm research staff at NCCID, and I will be your moderator today. The NCCID is funded by the Public Health Agency of Canada to provide knowledge and evidence for use in public health planning, programs, and policies related to infectious diseases. We are very pleased to be co-hosting this series with the agency. A quick disclaimer, the views expressed today do not necessarily reflect the views of the agency. I am joining you today from the city of Hamilton, situated upon the traditional territories of the Erie, Neutral, Rouen-Wendat, Haudenosaunee, and Mississauga peoples. This land is covered by the Dish with One Spoon Wampum Belt Covenant, an agreement between the Haudenosaunee and the Anishinaabe to share and care for the resources around the Great Lakes. Today, Hamilton is home to many Indigenous peoples from across the Turtle Island. We honor the Indigenous peoples who have lived on and cared for these lands for generations. We are grateful for the opportunity to share and call this place home. The Surveillance Advances Seminar Series has welcomed participants and presenters from coast to coast to coast since our inception in September 2023. While surveillance is the most common term used in public health to describe the process of tracking health events and determinants through the collection, analysis, and reporting of data, due to concerns over its connotations, some have suggested the use of other terms, such as public health assessment. We acknowledge that there is still an ongoing dialogue about the use of the term surveillance in public health. For the time being, without a widely accepted term in the literature, we would like to note that we use the term surveillance in the series title to refer to the assessment of and response to public health threats as a core function of the public health systems. Now, before we dive into today's seminar, there are just a few housekeeping items I would like to mention. First off, a recording of the seminar and presentation slides will be available shortly after the seminar on the NCCID website. That's nccid.ca under webcasts. Second, the chat box for participants has been disabled for this session. The hosts will use the chat box to communicate additional information with you. If you have any technical problems with Zoom during the seminar, please email us at nccid@umanitoba.ca. And finally, please send in your topic-related questions using the Q&A tab, and we will try to address as many as possible in the discussion period after the presentation. You can like any of the questions to push them up in priority. We would also like to note that Surveillance Advances is a Section 1 self-approved group learning activity as defined by the Maintenance of Certification Program of the Royal College of Physicians and Surgeons of Canada. The seminar series is also approved by the Council of Professional Experience per Professional Development Hours for members of the Canadian Institute of Public Health Inspectors. If you require a letter of participation for your attendance today, please look out for the survey that will be shared after the seminar. And now I would like to introduce and welcome today's speaker. Dr. Zara Nia is a research associate at York University and a data scientist at AI for Pandemic and Epidemic Preparedness and Response, or AI for PEP Global South, specializing in machine learning, data analytics, and natural language processing. Holding a PhD in computer engineering, Zara has spent 3 years as a postdoctoral researcher at York University, where they have developed a novel early warning system for respiratory infections through web-based data sources. Zara's primary research program is centered on the integration of artificial intelligence and data science to enhance decision-making processes in clinical public health. Through the development of advanced machine learning models and data mining methods, she aims to address complex health challenges by providing data-driven insights and predictive tools that inform healthcare policies and interventions. Outside of academia, Zara is invested in the development of large language models with the potential to offer anonymous medical consultation support to individuals, broadening access to reliable health information while maintaining privacy. She is deeply devoted to bridging the gap between cutting-edge AI technologies and practical healthcare solutions, aiming to create tools that empower both individuals and healthcare providers. So, thank you so much for joining us today, Zara. The floor is yours.
Thank you very much. Yes, hello everybody. My name is Zahra. I'm gonna be presenting how we built a surveillance, early warning, and forecasting model for avian influenza, the data sources that we used, and how much each data source contributed to the accuracy of the final model. Yes, next slide, please. Before I start, I'd like to thank my immediate supervisor, Professor Jude Kong. And we are affiliated by University of Toronto, by AI for PEP, and by academic. Next slide. I'd also like to thank our founders, the founders of our work. Next slide. And also we have a great avian influenza team that I'd like to give special thanks to them. We had Dr. Doris, Dr. Murray, and Dr. Emma joining us from Canadian Animal Health Surveillance System. And we had Professor Nicola, Dr. Itlala, Professor Nelson, Dr. Emmanuel, Oscar, Snow, and Toa also joining our team. And I'm very grateful for them. Yes, next slide, please. And yeah, we declared no conflict of interest. And next slide, please. Okay, so recently Canada is facing avian influenza, and it's becoming a critical issue to public health. And avian influenza, it has two basic categories: low pathogenic avian influenza and high pathogenic avian influenza. And recently, HPAI has emerged in Canada. So HPAI, it mainly occurs in waterfowls, but it can be transmitted to mammals, including humans. And it has a mortality rate of 52%, and the symptoms include cough, sore throat, fever, and diarrhea. Next slide, please. So here in the diagram on the right, you can see the outbreaks of avian influenza in Canada. So you can see, like, before November 2021, we had very few outbreaks of avian influenza, but since November 2021, there has been multiple outbreaks of avian influenza in Canada. And so it's not only in Canada that this is happening, in USA and also in the whole world. It is happening, but it's becoming more of a threat. And in November 2024, there was one human case of avian influenza in Canada. And this is all showing that how much we need a surveillance system for avian influenza. Next slide, please. Yes, so this all shows that how much we need for a stronger surveillance system for avian influenza. So avian influenza, as I said, it primarily happens between birds and waterfowls, but it can be transmitted to humans very rarely. But it has been reported that avian influenza has transmitted between humans, from human to human. And so there is a risk of a pandemic, but more important than that, avian influenza puts a great burden on the economy in the poultry farms and for bird farms. So it is very important to bring it under control. And the recent outbreaks, they had some characteristics that was different from the previous outbreaks. First of all, they covered a wide range of areas, like maybe on the global level. And then before, it only happened between birds, but right now it's transmitting from birds to mammals. This is happening more than before. And also, it has put a lot of burden on the economy, and we can see the concern on egg prices. So it's becoming more of an issue. Next slide, please. And there's a need for a strong surveillance system. So traditional methods, they mainly include um, studying the environment for surveillance, like studying dead or sick birds, whether domestic or wild birds, and analyzing the soil, the water, air, cages, feeding areas. So here, these methods, they are very expensive and they are very time consuming, and they need a lot of manpower. And the results, it is ready with a delay. It is ready and reported with a delay. Next slide, please. So we're looking at other sources that could be used that have a lot of advantages. We're looking at web-based data that could be collected through scraping web pages or through RESTful APIs. They are beneficial because they can be collected with less effort, like with several lines of code, with less manpower. They are faster. And the final report could be ready in real time. So this means that the forecasting model could prepare the results and report it much earlier. And such examples of such sources of data include Google Trends, like the number of times people have searched for keywords such as avian or bird flu in the Google search engine, or the number of news articles that have been released in this area, and the number of posts on social media platforms regarding avian influenza. Next slide, please. So yeah, as we said, these sources of data are very beneficial to traditional sources of data. So using these sources of data, we aim to build a forecasting model. And they can also be used for surveillance of avian influenza. So at the core, so we're building an early warning system. At the core of an early warning system, there is a predictive model. So we're using time series prediction. In this method, we always look at the past to predict the future. We see what was the trend and the pattern in the past, and we try to use that to predict the future. So the first data source that we need is the actual number of cases or outbreaks of avian influenza that has happened in the past. But that may not be the only source of data that we can use. Other sources, as we discussed, like Google Trends or social media activities or news articles, they can also be great indicators, and we can include them in our forecasting model to build a stronger model. And also, due to their benefits, we can also use them, take advantage of them for surveillance. Yes, next slide, please. So our contribution, it's threefold. First of all, we introduce new sources of data. So as you can see in this figure, we are getting data from multiple sources and we are combining them. And then we build a forecasting model. So our second contribution is that we build a forecasting model for avian influenza. And finally, we're gonna study how much each of these sources of data are important for the forecasting model, how much they contribute to the accuracy. And our research could be very beneficial first of all, for policymakers, and then for poultry and farms, and to bring the outbreaks under control and to minimize the economic loss. Next slide, please. So our methodology, it includes a machine learning pipeline that has 4 stages: data ingestion, data validation and pre-processing, training and testing, and train and test formatting, and training and evaluating the final model. The thing is that this pipeline, we made it automatic. We made all the stages happen automatically through programming languages. And we used in the data ingestion phase, we used several data sources: historical data, Google Trends, GDELT, Google News, Reddit, Facebook, weather and air quality. And we're going to go through them and explain them. And the benefit of these data sources is that they are all available through RESTful APIs and through web page scraping. So basically, it doesn't need human intervention. We can automate the whole process. Next slide, please. So first of all, the actual number of cases or the number of outbreaks, we got that from our source was the Government of Canada. It regularly releases a data set on the number of outbreaks. So this data set, it is on daily basis, and then it provides the number of outbreaks, and it provides the collection date. So basically, it's not the reporting date, it's the collection date. So we can trust that the number of cases is at the actual day or actual time which the incident happened. Next slide, please. So that's basically our historical data. Another data source that we use is Google Trends. So basically, when the number of cases increase and people see that like happening, they go and search about it. When they see it in their environment, they go and search about it. And usually when a disease, an outbreak happens, the number of searches in Google on that particular disease increases. And usually these two have a correlation. As we can see in this figure, the pink line, that is the number of avian influenza outbreaks. And then the blue line, it is the Google Trends, or the number of times people have searched for avian influenza. We can see that they have the same pattern and the same trends, and they are correlated. Their correlation is very significant. So this seems to be a good data source that we can use for both surveillance and for building our forecasting model. But other than Google Trends, we also use the first and second derivatives of Google Trends. So basically, the first derivative, it shows whether the trend is increasing or decreasing, and the second derivative shows how fast it is increasing or decreasing. So basically, the first and second derivatives, they also carry important information, and by experience, we found out that including them would increase the accuracy of our model. So we included them in our data sources for building our forecasting model as well. Next slide, please. So other than Google Trends, another data source that we used was Google News. So Google News has an API that it gets the country and a set of keywords at its input, and then it returns all the news that has been released in that country regarding that particular topic. So we, using Google News API, we gathered all the Google News that were released in Canada, and they were about avian influenza, and we found their volume, and the volume was significantly correlated with the number of outbreaks. So in this diagram, the blue line is the number of outbreaks, and the pink line, that is the volume of Google News. And you can see that they also have the same trend, and they are also correlated. So basically this means that Google News or the number of news released is a great source for surveillance, for disease surveillance, and also it can be a great indicator that we can use in our forecasting model. Next slide, please. Another data source that we used was GDELT. So GDELT, it also provides all news articles that were released in a particular country. So it includes broadcasts, online news, media, television and radio news articles, and also academic reports. And so we gathered the volume of news articles related to avian influenza that were released in Canada, and also we saw that that is significantly correlated with the avian influenza outbreaks as well. So as you can see in this diagram, the blue line, that is the outbreaks, and the pink line, that is the volume of the news articles that GDELT returned to us. We can see here that they both have the same pattern. They are significantly correlated. So this is also another great source that we can use for surveillance and for building a forecasting model. Next slide, please. And so we talked about Google Trends, we talked about news articles. Now we're going to talk about social media activity. So we looked into Reddit and Facebook. For Reddit, we looked into subreddits related to Canada. So you can see a list of the subreddits here. Yeah, subreddits related to Canada or different provinces of Canada. And then we searched for all the posts that had keywords related to avian influenza. So we also found that the volume of the post, it is significantly correlated with the outbreaks. So here you can see the blue line, that is the outbreaks, the avian influenza outbreaks, and the pink line, that is the number of Reddit posts that we gathered. You can also see here that they both have the same trend and they are significantly correlated. And yeah, we use that in our forecasting model, and also it could be a great source for surveillance as well. Next slide, please. And then Facebook. So we searched into Facebook pages that were related to farms and poultries in Canada, and we searched for posts that had any of those, any of the keywords, any of these keywords here that are related to avian influenza. And although the number of posts were very sparse, like you can see they are very sparse, but still they were correlated and they had the same trend. So Facebook also can be used for surveillance of avian influenza. Again, in this figure, the blue line is the number of outbreaks and the pink line is the number of posts on Facebook. And yeah, it was significantly correlated, and we use that in our forecasting model as well. Next slide, please. And so another data source that could be very beneficial, especially for respiratory infections, is air quality and also weather data. So here I'm going to talk about air quality. So air quality was gathered from Sentinel 5P mission of Google Earth Engine. And we gathered two parameters, carbon monoxide and also UV index. So the thing is that Google Earth Engine has an API. So this can also be gathered through programming languages and automatically, like without the need of humans. So we gathered this data, and we surprisingly saw that it has a negative correlation with avian influenza outbreaks. So here you can see the blue line is the number of outbreaks. In the top diagram, the pink line is the concentration of carbon monoxide, and the lower diagram, the blue line is the number of outbreaks, and the pink line, it is the UV index. And yeah, we can see that it has a negative correlation. So basically, this means that when pollution increases, we have less avian influenza. And the reason could be the migratory birds. When we have more pollution, less migratory birds appear, and therefore we have fewer number of outbreaks. So also, so you can see that air quality is also an important factor that we can use for both surveillance and for both forecasting. Yes. Yes, next slide, please. And weather information. So we also used minimum temperature. So we gathered this data from OpenMeteo. OpenMeteo also provides an API that we can use it to gather historical weather information. And also it also provides real-time weather information as well. So So the correlation is significant. It is significant. Also, in our forecasting model, we found that minimum temperature is an important factor that plays an important role in the building that final accuracy. So minimum temperature also could be an important factor for surveillance and also for building the forecasting model. Next slide, please. Okay, so this was about our data ingestion phase. I'm going to move forward to the data validation and pre-processing. So once we gathered the data, we used it for in different machine learning models. So here you can see the list of the machine learning models that we used. The first four models, they are deep learning models, GRU, LSTM, CNN GRU, and CNN LSTM. And then the next three models, they are some basic machine learning models, random forest, support vector machine, and naive Bayes. And we compared the accuracy, and eventually we found out the eventual result was that GRU works the best. But what we did with our data to be able to use it for these machine learning models was, first of all, to integrate them and then to remove the missing values. So the missing values was interpolated by averaging the previous and next values. And then also we had to scale our data because by experience also we found out that if we scale our data, the models work better. It was only for random forest that we didn't need to scale the data. For other models, it worked better when we scaled our data, and we used min-max scaler for this purpose. Next slide, please. And train and test formatting. So we have our data, and now we need to prepare it to insert it in our machine learning models. So basically, we had to build our observation. We needed a sequence of previous incidents, like previous time series, whether it's historical data or any other any other data sources. We needed a previous sequence of data, and that was inserted in the machine learning model, and we used that to forecast the next 14 samples or the incidents in the next 14 days. So basically the next a sequence of length 14, this was used as the labels. So we built this will build one observation. And then we build our observations and we build the whole data set. And then we divided it into training and testing sets. So 2/3 of it was used for training and 1/3 for testing. So this was the basic steps that we needed to take for the deep learning models. For the machine learning models for random forest, support vector machine, and also naive Bayes, we needed to integrate these different data sources. So we used a principal component analysis for that purpose. And yes, next slide, please. And then the next stage of the machine learning pipeline, which is training and evaluating the models. So yeah, the data sets were inserted, the inputs were inserted into the machine learning model, and then the labels were also given to it, and the model was trained and tested. So for the deep learning models, their advantage is that we only need to train only one model but for the basic machine learning models, for each 1 to 14 step ahead prediction, we need to train a different model. So basically, this means that deep learning model, they are faster. And so this is their first advantage. And also later, I'll talk about other advantages too. And so for the evaluation, we use two metrics, root mean square error and correlation. Next slide, please. So here is a summary of our results. You can see that basically the deep learning models worked better than the basic machine learning models. And among the deep learning models, GRU was the best one. It has the highest correlation and the lowest root mean square error. So here you can see the results for 5 days ahead prediction and 14 days ahead prediction. Next slide, please. But also we have visualized it for 1 to 14 days ahead prediction. And you can see that how different models perform for different days ahead predictions. For correlation, you can see that the highest correlation was gained using GRU, and for root mean square error, the lowest error, it was obtained again for GRU. So GRU worked the best among all of the models. Next slide, please. And this is our results for GRU. So in these diagrams, the black line, this is the actual outbreaks, and the pink line, that is our forecast. This is the GRU forecast. So you can see our results for 1 day ahead, 5 days ahead, 7 days ahead, and 14 days ahead. You can see how closely the forecast moves, how close it is to the actual outbreaks. So I believe this is a really strong model for forecasting the avian influenza. Next slide, please. So what we discussed was on country level, but also we tried to build our model for a regional level as well. So we worked on 3 regions in Canada: Western, Central, and Atlantic, and we excluded the territorial region because first of all, there aren't that many avian influenza cases in those provinces, and also because there isn't enough data for those provinces. Like we had a lot of missing values there. So on the left-hand side figure, you can see the number of avian influenza cases in different provinces and in different regions. Next slide, please. So the first step was to find our data sources for different regions. So we were able to do this for Google Trends. We were able to separate the Google Trends for different regions. But that wasn't possible for Google News because Google News API, it returned the data on country level. For Reddit, since we had subreddits related to different provinces, we were also able to separate the data for different regions. The same for Facebook, we had pages related to different provinces. And also air quality data, we had that on very granular level. So we were able to find that for different regions, and also for weather data or minimum temperature, we were also able to find the data for different regions. For GDILT, again, our data was on country level. We were not able to separate it for different regions. But anyways, we saw that our data was mostly correlated with the outbreaks on regional level. So here you can see which data sources were significantly correlated with the avian influenza outbreaks in different regions. Next slide, please. And again, GRU worked best on regional level too. So here you can see our results on regional level. So in these diagrams, the black line is the actual number of avian influenza cases, and the pink line is the prediction. So here the first column is for 5 days ahead prediction, and the second column on the right is for 14 days ahead prediction. The first row, it is for Western region. Then the next row is for Central region, and the next row for Atlantic region. And for all of them, you can see that the predicted line is very close to the actual line, and it can also actually be used for prediction. So yeah, so we have built a strong model. Next slide, please. And the next step is to find feature importance. So for feature importance, we use the permutation method. So in this method, we repeat the training and testing process several times. And each time we permute one of the data sources, and we see how much the final accuracy degrades. So that degradation, that shows how important that data source is. And so we have two different evaluation metrics. So we use both of them. We perform the permutation method using both of these metrics. And for each data source, or basically for each feature, we use 10 different permutations, and then we compared different features using the Mann-Whitney U-test. Next slide, please. So here you can see our results. So one thing that we can see here is that historical data, it has a higher value compared, or a higher value compared to other features. And so basically this shows that historical data plays the most important role in building the final accuracy. But after historical data, it's Facebook that is significantly higher than other data features, and also minimum temperature. I could say these two are the most important features. But and then the other data sources, they are very similar, or at least their difference is not significant based on Mann-Whitney test. Yes. Next slide, please. So we have actually built our platform. So we have built a website that shows our forecast in real time. So if you use this QR code, it leads you to our platform. You can use it to go to our platform. Yes. Next slide, please. So in our platform, first of all, we have a map. So you can see that it is actually, it shows our prediction until 5th of June. And so for now, the number of outbreaks that it shows is very low. Like, it's not predicting anything serious is going to happen. If I compare it to before, it has increased a little bit, but I believe the outbreaks are, like, they usually happen in November, and it's not right now. Yes, next please. So this is the forecast for different regions. And next. And this is the forecast on country level. So both on regional level and on country level, it is not predicting anything serious yet. Next, please. Next slide. So other than the actual forecast, it may also be beneficial to look into our data sources, because as we said, they are correlated with the number of cases. So they're not showing the future, but they can be used for surveillance. So this is for Google Trends. Next slide. This is for Google News. You can see that more and more news are being released on avian influenza, and it's just becoming a more of an issue. Next slide, please. This is for Reddit posts. Yeah, as I said, the volume of posts on Reddit and generally on social media, that is also a good source for surveillance. Next slide, please. And this is for GDILT, the volume of news that GDILT shows us. yeah, this is also a good source for surveillance. Next slide. And this is the actual number of outbreaks, avian influenza outbreaks on country level. So yeah, we can, in our platform, we can compare the different data sources with the outbreaks, and if there's a threat, probably if we see that the number of news articles or maybe Google Trends is increasing, if we see that the trend is increasing, we may suspect that there may be an outbreak ahead. Next slide, please. Yes, so to wrap up, what we did in this work was to introduce new data sources for surveillance of avian influenza, and also we used those data sources to build a forecasting model, and eventually we used our model to see which of the data sources are more important in building that final accuracy. But our data has our work has some limitations. First of all, we have limitations in our data. Because we looked into Google Trends, we looked into social media data, but usually normal people come and like search. It does not reflect data from, for example, farmers or poultry workers. They are the minority. So maybe in the future, people could also, or researchers could also look into private Facebook pages or maybe subreddits that are only for farmers or poultry workers, maybe bringing those under consideration that could give further insight on what's really happening. And then another limitation is that, so here we were able to collect the historical data and build our model, but in practice, when we really want to implement it, there is a delay. Historical data is not reported in real time, and that may affect the accuracy of our model. So that's something that we should bring under consideration. And finally, there are other data sources that could be helpful. For example, wastewater data. Researchers report that they can predict respiratory infections 14 days ahead or even more, but they are not available. And even if they are available, they are not available through RESTful APIs or web pages. So so this whole thing, it could be improved. There is space for improvement if we be able to collect the right data and then also build better models. Next slide, please. And then we should also mention that to build this model, we need strong hardware, we need reliable storages, and also we need GPUs to build the model. And so we need some resources to build the model, and only the result could be consumed by edge devices. And there are also space for future work. So we mainly worked on temporal level. It is also possible to work on spatial level to find the hotspots. So we have actually started doing that as well. Maybe I'll discuss it later. And it is also beneficial to look into social media and just to see what are people's concerns, what is their fears, what are mass opinions regarding avian influenza, and also do topic modeling and sentiment analysis, and see recognize any mis or disinformation on social media. And yeah, and as I said, it could also, future works could also consider focusing on private Facebook pages or subreddits. Next slide, please. And another thing that is important is that in the current outbreaks, there are more and more mammals are being involved, cattle and mammals, and so this research hasn't started yet, but it is important to also do research on mammals that are infected with avian influenza, like to understand what is their hotspots and what environmental factors contributes to the appearance of avian influenza in mammals and cattle. And then maybe do some gene analysis and find like what strains are transmitted to mammals and cattle. And also, there is a need for regulations. So we have some regulations for poultry and industry to keep them safe. But soon there will needs for regulations for mammals, for maybe pets, because many of the times even like dogs and cats get the avian influenza. So maybe there is a need for regulations for mammals as well. And also it is important to consider climate change, because climate change, it shifts the migratory birds patterns and where they appear, and that would definitely affect the temporal and also spatial pattern of avian influenza. So also studying climate change and how that affects avian influenza in Canada or even different locations, that's also a research that there's a lot of space for research here as well. Yes. Next slide, please. So as I said, we have worked on spatial level. We have tried to find the hot spots and cold spots of avian influenza. So here you can see the red parts, they are the hot spots, and the blue parts, they are the cold spots. And in future, we're going to build dashboards that we can see their hotspots live. And also we have tapped into social media to understand, to analyze people's posts and do some NLP on them, do topic modeling, understand fears and concerns, and also do emotional and sentiment analysis and find dis and misinformation. And hopefully we could share that on our dashboards as well too in real time. Yes. Yes, next slide, please. Yes, thank you very much for listening.
Thank you, Zara, for sharing your expertise and knowledge on using digital-based surveillance to track and anticipate avian influenza outbreaks. We will now begin our discussion period. So please send in your questions for Zara using the Q&A tab. I see we have a queue already. You're invited to ask questions in English for a live response, and any questions in French we will try to follow up with after the seminar. Just a reminder, you can choose to upvote other people's questions. Everyone is welcome to participate, and we'll try to address as many as possible in the next 10 minutes, but we may not get to all of them. So to start us off here, we have an upvoted question from David. Are there any confidence or credible intervals around the predicted cases? If yes, how broad narrow are they?
So I believe like you're talking about accuracy and yes, the confidence interval. So definitely there is, and yes, you saw our results. So the correlation was around 60%, and also the root mean square error. So that I definitely, we can look into the confidence interval. That is something that I can add maybe in future. Yeah, that's something that I can add in the future to my research. Yes, of course. I'm not sure, like, yeah.
We have another highly upvoted question from David. Have you tried to forecast using only official reports by the Canadian government? If yes, how did it compare to forecasts informed by social medias, news, etc.?
So as I said, using social media and news articles and also Google Trends, that did increase the accuracy. As I remember, only historical data that the correlation was below 50%. And by adding the other data sources, like each data source, it actually increased the accuracy, and gradually we reached to 60%. So yes, we did try that. And yeah, definitely using those other data sources did increase the final accuracy of the model. They can definitely be used in forecasting models. Yes.
Thank you. We have a question from Joseph. Is it possible to apply this research by gathering Africa data?
Actually, we have tried in Africa too. Actually, we have um try to build a forecasting model for COVID-19 and influenza in Africa. And there are some limitations there. For example, people in Africa, they are mostly active in Facebook. So probably data from Facebook could be used. And there is like we can gather Google Trends, but you got to know that there are limitations. Like maybe many of them, many locations, people don't have access to internet. So there are some limitations, but we have successfully done this for COVID-19 and influenza in Africa, and it is possible. We can try for avian influenza too and see how that works. Yes.
Thank you. Up next, from Banjo, what API do you use for epidemiological data?
So the I believe you're talking about the historical data, the number of cases. So that is released regularly by the government of Canada, and it is in a CSV format. It's a CSV file. So you can just write a code in Python that gets that CSV file and updates the data. Uh, so for historical data, I think I had the link in my slides. The government of Canada releases the data in a CSV file. So actually, yeah, it is. For that, we can just use that CSV file.
And excuse my mispronunciation, we have a question here from Chao Quan Yao. What is the rationale for you to use Google Trends and their first and second derivative together for machine learning? The derivatives are correlated with the original data. If it is beneficial to use them, why did you not use them for other sources?
So yeah, we used that for Google Trends because we saw that it increased the final accuracy of the model. There were other data sources that we used, but then we didn't see, like it didn't increase the final accuracy, so we just excluded them. And yeah, we use that for Google Trends because they carry important information and they did increase the final accuracy of the model. As I said, because the first derivative shows if the trend is increasing or decreasing, and then the second derivative, it shows how fast it is increasing and decreasing, and they improve the final accuracy. So we did include them in our model, and we did include them in our forecasting model.
Thank you. Just another question from Adesina. Why was the projection only for 14 days? They ask, why not for 3, 6, or 12 months?
So in our diagrams, or generally when we do forecasting model, like it is it has a great accuracy for 1 day ahead, 2 days ahead. Then eventually, as we go further, the accuracy decreases. Like the 14 days ahead, the accuracy is lower than the first day ahead. As we go further, like the further the model is able to predict, the stronger it is. So at some point you got to stop. Like you see that, okay, the accuracy is not acceptable anymore, and you got to stop there. So for now, I can say that our model works good until 14 days ahead prediction. Yes.
Another question. This is from Katwana. Are you aggregating data from different data sources into one data set? Why did you choose to train multiple models? Do they have different purposes, and how?
So basically we just wanted to compare them and choose the best one. Like I see that it's not always like GRU works better than the other ones. Many research, LSTM works better. So in our work, we found that GRU works better. So basically, we just wanted to see which one works better and then choose the best one. And just to talk a little bit about data integration. So for deep learning models, they are multivariate. We built a multivariate forecasting model. Like we just put these data sources together in a matrix, and then we converted into tensor, and we were able to we took a sequence of the previous incidents, and we were able to insert that to the deep learning model. But for the machine learning models, so basically they're mostly univariate. I'm talking about random forest support vector machine and naive Bayes. So we have to somehow combine them together, and we use principal component analysis to combine them. And we took the first principal component, and we used that for forecasting the avian influenza outbreaks.
Thank you. This is another question from Bajo. Are social media essential to identify hotspot zones? What other data do you need for that, in addition to epidemiological data?
Um, so we can only use historical data. But we used other data sources because of their benefits. Because first of all, they increase the final accuracy, and then secondly, we found that they are correlated. They have the same trends, the same peaks, so they can also be great source for surveillance. And because historical data, it is reported with a delay. Like I think at least 2 weeks of delay is present for historical data. But social media data, we can have access to it in real time. Like we can know how many people have posted on avian influenza yesterday. So that may be a better source for surveillance. If we don't have access to the historical number of cases, these are alternatives that can give some insight and some idea of what's happening. If there are a lot of activity, maybe there's something happening. And yeah, also in our forecasting model, adding them increased the final accuracy. So why not use them?
And for our last question, Joseph says, thank you for your great presentation. Please, I would like to know the motivation of using those machine learning models in your work.
Yes, so we used GRU LSTM, CNN GRU, CNN LSTM, and then we used some basic models. So basically, our goal was to compare these different models and see which one works best and choose the best one. And we see that this happens, like it is very normal in research to compare different models with each other and choose the best one. So yeah, that was basically what we did, was to choose the best one out of all of them.
All right, that ends our Q&A period. Thank you so much, Zara, for your thoughtful responses. On to our next slide, please. So thank you everyone for joining us for today's seminar of surveillance advances, and to our speaker, Dr. Zara Nia, for their fantastic presentation. A quick reminder that the recording for today's seminar and the presentation material will be accessible for viewing on NCCID's website in a few weeks. Please take some time to complete our survey for this presentation. You can scan the QR code on this slide to access the survey, or look for the link in an email that will be shared shortly. In the post-seminar survey, you will also be able to request a letter of participation for your attendance today. Please join us for our next seminar on Tuesday, June 24th from 1 to 2 p.m. Eastern Time or 12 to 1 p.m. Central Time. If you have any more questions about the Surveillance Advances seminar series, please visit our webpage at nccid.ca/Surveillance Advances Seminar Series for more information. That concludes today's seminar. Thank you all for joining.